Hey, don't forget to have it be.
Okay.
Gross.
All right, phones away. Phones away. In pockets away.
Jeez, I don't know.
All right, so here's the plan. What I want to do today is two things. I want to quickly review for the third part of chapter 6 of that, the graphic calculator part. And then I want to just extend what we talked about the other day a little bit. The chapter 6 stuff, we're going to kind of extend to chapter 7. We're going to very briefly cover the chapter 7 stuff. I'm not going to go into a lot of detail, but I want you to just see the basic concepts and get some practice with some of these rules of rational exponents and things like that. But we're not going to do a heavy-duty approach to this. Okay, so first of all, graphing calculator stuff. We're going to do two things at once here. We're going to focus on graphs of polynomials. At the same time, we're going to kind of learn or practice using the graphing calculator. Before you go into next year, especially if you're going to college, I want everybody to really have a good handle on how to use these things. Yes, sir?
On one of my assignments, it said choose the corresponding graph, and there was no equation. It was just graphs.
Like, on this one, was it one like this?
Yeah, no, it didn't even have an equation.
It just said the corresponding graph is?
Yeah.
Yeah, there's the one from the book.
Oh, the ones from the book?
I don't even have a book.
Oh, yeah, those are right. Those are the ones from the book, yeah.
Okay.
So it's just gonna give you a section, it'll say like 7.6 or 7.5, number 13. So it's section 7.5, and that's the number of the book.
Okay.
That's the graphic. Okay, that explains it. Okay, so a couple things about this. We talked about this earlier. You might remember what we said was if we can find the zeros of a polynomial, these are already factored, so that'd be easy to do, right? If we can find the zeros of the polynomial, those correspond to x-intercepts. And then all we'd have to do is test values, x values, between the x-intercepts and outside of the to the right of the furthest to the right x-intercept, I said that was really clumsy. The x-intercept that's furthest to the right, we want to pick a point that's further outside of that. Same thing for the left. Whichever x-intercept is furthest to the left, we pick one that's a little bit further to the left than that. And the point being, if we choose those x values and we plug them into the function, we just want to know is the function above or below the x-axis, and that's telling us if it's looping up or down between each x-intercept. Okay, that's good to know how to do. On the test, I have chosen to make this portion of the test graphing calculator friendly. In other words, you have the availability of a graphing calculator. So you may graph these things. This is an important skill though. If you're going to want to know which of these functions corresponds to that graph, you've got to be able to graph the function in a way that you can tell, right? So all you're really going to do here is literally just enter that function. You don't have to simplify it, just leave it the way it is. The calculator does not need it to be simplified. So we would just, in this case, put in 1/10 quantity x plus 3 times quantity x minus 1 times quantity x minus 4. Okay, make sense? And then we just we don't just hit graph. We just hit graph, we're kind of at the mercy of whatever our window was set at. Let's start off by going maybe zoom standard. And then we can take it from there. Now that's not a bad window for us, but we got to know how we could change the window, right? You know that x min is the left edge of the screen, so if I wanted to bring that in a little closer, instead of -10, I could choose like -5,
How did you
right?
get to that?
I just graphed that. I entered that. Okay.
But like how?
Oh, and then zoom 6. Zoom standard just resets the window to its normal starting place every time. And then you can tweak it from there. Okay, like I say, if we wanted to kind of focus in on the action in the middle a little bit more, where the x-intercepts are and the peaks and the valleys, we could go into the window and maybe go from, instead of -10, we could make it -5 up to about +5. And then it moves us in a little closer to the part that we want to be able to identify points on, right? I don't need to have it, the y be so big either. Instead of going from -10 to +10, we could just go from like, how about -4 to +4 for the y? So the bottom of the screen would be at y equals -4, and the top would be at y equals +4. Something like that. Oops. That's pretty good. Now we get a really good idea what's going on. So we're looking at a couple things here. If I want to identify this graph, I want to find something that has that shape. It sort of looks like that one almost, maybe, right? It's possible. Well, I guess it's not. It looks close to it, but it's not. It's a little different. So to find exactly which one it is, we could just go identify some key points. Like we could find, for example, where that 0 is. Okay, we could do that exactly by going second calc 2. And then it's going to want a left boundary and a right boundary and a guess. So we got to surround the 0 and make a guess in between. And it'll tell us the exact coordinates. We probably don't need to do that here. We can just count over and see that that one's at about -3. This one looks like it's at +1, and that one looks like it's at +4. So that's helpful. What if I want to know the coordinates of that peak up there? Of that, that's what we call a maximum, or it's just like a peak on a mountain. That's a minimum or a valley. If I want to know where that maximum is, look at the menu. Which option?
Maximum.
Yeah, 4, maximum, right? So I could choose 4, and then it's just like you'd expect it to be. It wants a left boundary, so we'll move the cursor over there somewhere to the left. Right boundary, we'll move it over where it is now maybe, so we can trap it between those boundaries. We can only have the calculator look between the boundaries to find the maximum. So let's do that. So right about there, let's say, left boundary. Right boundary, my guess. Just, somewhere close to the top. And it tells us it's at -1.36, +2.07. So we can find the one that has about those coordinates then too. See what I'm saying? Find the graph that looks like that. Well, you tell me. Let's just scroll through them and tell me when you think you see it. That's it right there, isn't it? See, -3, +1, +4. It looks like it's about a little more than, about -1.3 is about, that's about right, isn't it? That make sense? All right, so that's how we could do those.
Will we be in the lab tomorrow?
Yes, tomorrow and Friday. Yeah. Oops. Okay. Okay, what about these? These guys that say they want you to describe the end behavior. That's what this means. What's the limit of the function as x approaches -infinity? Just we want to know, in other words, -infinity on the x-axis would be clear out there, right? When we go clear out to the left, what does the function do? There's only two possibilities. What's it going to do? Either the function, when I go clear out there, is going to do what? It's going to go down, or it's going to go up, right? Infinitely high or infinitely low. So the answers are either going to be infinity or -infinity every time. It's just a matter of which one. How do you tell? Well, you just look at the sign of the dominant term, the leading term. So if we just focus on this guy right here. So the leading term is 2x cubed. The other ones are going to be tiny compared to that one. What's the sign going to be? Well, when x approaches -infinity, wouldn't you agree that x is negative, right? So if x is negative, what is x cubed gonna be?
Negative.
Negative, everybody agree? So x cubed, when x is negative, x cubed is negative, right? 2 is positive or negative? Positive. So we get the product then of a positive factor times a negative factor equals what?
Negative.
Negative. So the answer is negative infinity. Okay, good enough? The other way we can do that is on a graphing calculator. I don't think you need to, but you can if you want to check it at least. Okay, if I graph that function, and I really only have to graph the leading term, I don't even have to graph the whole thing. I'll just graph the whole thing, but it's unnecessary, you don't have to. Leading term determines the behavior. So if I graph that thing, let's graph it where we can see a little further out to the sides though. Instead of just negative 10 to 10, let's do something like go, negative, 25 to positive 25. And we'll just go zoom 0. So we'll let the calculator pick the y. So we picked the x's. Now you can see the behavior, right? We can kind of see what's going to be happening. As we go far to the left, it goes down, doesn't it? Right? So that's saying, look what this is saying here. As x approaches negative infinity, f of x approaches negative infinity. Everybody see that? Because it's going down. Make sense? Okay. What would the answer have been if we would have been approaching positive infinity?
Positive.
Positive, right? In that case, when we go to the right, we go up, so it would have been positive infinity, right? Okay? All right, whoops. All right, moving on. So here's some other ones. I'll just, what's easier for me just to graph these. Okay, how about those? These are on the graphing calculator part of the test because they go with the graphs, but they're not really graphing calculator questions. What were they on? If you're supposed to build the simplest function from those zeros, how do we do that? Do you remember? What do you think? Yeah.
Just go x minus 9, x minus, like in a different parentheses, x minus 9, and then go to x minus 5, then x plus 5.
X plus 4, you mean?
Yeah.
Yeah, you're right. Now, why is that? Think back to, what we normally do is we start with a big polynomial, set it equal to 0, put it in standard form, we break it apart into factors, and we set the factors equal to 0 to find the zeros, right? So each factor produces a 0. Well, we're going to work backwards. Each 0 we're going to turn into a factor and multiply those out to get the polynomial, right? So what's the factor that goes with each 0 is the question you have to answer. And it's easy to do. You just subtract the zeros from x to find the factors, right? So this one's going to be x minus 9. That one's going to be x minus 5. And that one is x minus negative 4, so x plus 4. And f of x is just going to be the product of those three. FOIL out 2 of them, simplify, distribute the third, and that's it.
What about if it was like 4i?
Okay, so let's do one with an I. Yeah. So what about if these are your zeros this time? Guess I can do this again. So what if my zeros are, how about if they're positive 2, negative 3i? See, I give you those two. What do I have to do? Okay, so I'm good. Say it again. X minus 2. And yeah, x minus negative 3i. But what are we missing? There's a trick here. Yeah.
You got a 3R.
Okay, remember that the imaginary zeros must come in pairs, in complex conjugate pairs, right? So if we're told that negative 3i is a 0, then we also have, we don't have a choice, we have to include positive 3i, right? Yeah, it's, oh good, so then we're gonna get x minus 3i as the factor. And if now we're just gonna multiply these out. It looks like it'd be harder, but it's actually easier. It's easier to have these complex conjugates because they multiply together so easily. I'll show you, remind you, you probably already know this, but if we multiply complex conjugates together, what do we always get? So the complex number a plus vi times the complex number a minus vi, those are conjugates, always give us. You can just FOIL it out if you want to. What's I squared equal to? Negative 1, right? You have to remember that if you're going to FOIL these out by hand, but you don't have to. When you multiply complex conjugates together, you always get a squared,
Minus B squared?
no, plus b squared. The I squared turn it into a plus instead of minus. You always get that result. So when I multiply these together then, these complex conjugates, what's my a and what's my b in this pair of conjugates? A is what? X. A is the real part without the I. B is the coefficient of I, right? So it's going to be a 3. So I'm just going to get, when I multiply those out, a squared plus b squared. So x squared plus 9. Easy. You can FOIL it out and the terms will cancel and you'll get that result. That's just a lot quicker if you remember that. And all I have to do is just distribute the x minus 2, and we're done. Okay? So they really don't make it any harder when you have I squared. Okay, last issue. The game we're playing on the last issue here, the last kind of problem, I like these. These are sort of fun. I'm going to give you a shape of a polynomial function. And your job here, when you play this game, is to tell me what the minimum degree of the polynomial is, right? So how about this one? Okay, there are 3 kinds, actually maybe even more than 3. Do you remember what the 3 kinds of clues are? There are some clues about that tell us. What's one of them, Jake?
The curves.
Okay, the number of, wait, by curves you mean turning points?
The number of.
Okay, the number of turning points. Now, turning points are places where an ant walking along the function changes from going uphill to downhill or from downhill to uphill. So in other words, peaks and valleys. How many peaks and valleys are there? 2. There's a turning point there and a turning point there. Now, what's the rule? You fill in the blanks here. If a polynomial has 2 turning points, then the degree of the polynomial is at least 3. Good. It's got to be at least 1 more than the number of turning points. Okay? So 2 turning points tells us that the degree of the polynomial, we'll call it n, has to be greater than or equal to 3. 1 more than that. Okay? What's another clue? The number of zeros, number of real zeros, so the number of x-intercepts. So there, how many x-intercepts are there?
3.
3. So there are 3 x-intercepts. Tells us if there are 3 x-intercepts, the degree of the polynomial must be at least 3. It's got to be at least as high as the number of x-intercepts. So that tells us that n has to be greater than or equal to 3. And then another hint is the end behavior. Okay, the end behavior. What in the world? By end behavior, I mean even or odd. So even end behavior, what does even end behavior mean? What do you mean by that? Okay, either both of them go up or both of them go down out at the ends of the function, right? So in other words, they match. They have to match. They have to do the same thing. Odd end behavior would be if you're going like that or like that, right? One goes up and one goes down, right? So is this even or odd?
It's odd.
It's odd. So this is odd. So what do those clues tell you about the smallest degree this one could have? 3, right? All the clues say 3, don't they? Right? Could it be more than that? Sure, it could be 111. But the smallest it could reasonably be is 3. So that's the answer. Okay? Make sense?
So
Go ahead.
3, because 3 is the smallest degree.
3 is the smallest degree it could be. Yep. Okay, questions? Seem pretty straightforward? Yes. Yes. Okay, I'm gonna do another one. I'm gonna try to trick you.
Don't trick me.
Oh, I'm trying to trick you.
No, don't trick me. You don't like me there. Oh, I know this. 1. 1,
Okay.
0.
Okay, so let's look at this. What are our clues here? The number of x-intercepts, how many?
1.
1. So the number of x-intercepts says 1. That tells us n is greater than or equal to 1. How many turning points are there?
2.
None.
None.
What?
None of them
None,
are.
because there's the ant. Now think about your little buddy the ant that's walking down this function.
It's all going down.
Yeah, he goes downhill the whole way. He never goes from going down to going up, or from going up to going down, right? He's going downhill the whole time. So the number of turning points is also telling us n is greater than or equal to 1, right? 0 turning points, got to be 1 more than that. Okay, what's the end behavior, even or odd? It's odd. Okay, we get odd
Odd.
end behavior. So all those clues are pointing to this being n equals 1, is it? What does n equals 1 look like? A first degree polynomial is what? It's a line, right? N equals 1. If I have a first degree polynomial, that would be something like this. Y equals 3x to the 1 plus 5. That's a line, right? Is that a line?
No.
No, that is not a line. So if it's not a line, it's a curve. But it has to be odd, and it has to be greater than or equal to 1. What's the next available possibility? 3. 3 is the answer, right? It can't be even, but it's got to be bigger than 1 because it's not a line, so it has to be 3. Okay? All right, one more. How about... How many x-intercepts? 2. So that's telling us the degree is at least 2. How many turning points? How many? Christina, how many turning points? 1. Good. 1 turning point's telling us that the degree is at least 2. 1 more than that, right? So this tells us n is greater than or equal to 2. N behavior, odd or even? Even? Same on both sides? But I mean, but you're right, it's not, it's kind of goofy looking, but wouldn't you agree that the ends both go down?
Yeah.
Okay. So, what do all the hints point at? 2?
It's 4.
But it's got to be 4 because an n equals 2. Now think what that is. If n equals 2, that's a polynomial like this. Y equals 2x squared minus 3x plus 1, for example. What's that? That's a parabola. N equals 2 is a quadratic polynomial. We know from chapter 5 that the graphs of quadratic functions are always parabolas. Always parabolas. And parabolas have a distinctive shape. They're always symmetrical, right? That's lumpy. That's not symmetrical, right? So that can't be 2. It's got to be bigger than 2, but it has to be even, so 4 is the answer. Okay, see how it works? Tricky, right? Not for you guys. You got it. Okay, so now I want to take a look at I think I can make this really easy for you. I do. So just let me have your undivided attention for a little bit here. I'm going to really turn this down to just the essentials for chapter 7. And that's really all we need. And you'll get more practice with this next year. Okay, so here are the essentials. Chapter 7 it's just an extension of section 6.1, or at least this section of chapter 7, section 7.2, 7.1 and 7.2. Just a little extension to what we did last chapter. The rules we did last chapter, we only applied to integer exponents, but what if they're fractions? They're basically the same. So for example, what if we have something like x to the 1/3 times x to the 1/5? And from section 7.1 real quick, what does it mean to say x to the 1/3, by the way? What is a fractional exponent like that, even 4? What does it represent? How can I write that as a radical? Remember? It's the cube root. Yeah, it's the cube root. Whatever the number is in the bottom of the fraction, that's what we call the index of the radical. And that just tells us the kind of root that we're taking. So x to the 1/3 just means a cube root or a third root of x. X to the 1/5 is just a fifth root. That's all it is if you wanted to write them as radicals. But I would urge you not to write them as radicals, because if we do this product as a product of radicals, what's that? That looks like nonsense, right? It doesn't look like there's much you can do with that. But when I write them as exponents, if I write radicals as fractional exponents, now it's not so bad. We know how to do this. When I multiply like bases, what did I do in chapter 6? You add the exponents, right? Multiply like bases, you add the exponents. So we just end up getting the base x to the power 1/3 plus 1/5. That's it. Only difference being, yeah, sure, the fractions, but you guys are, you can do fractions, right? You're to a point now where you should be able to do these. I think you should be able to do these in your head. On a test, write them on paper, but otherwise, practice doing these in your head. What's my common denominator going to be?
15.
15. So 1/3 translates into how many 15ths? How many?
5.
Yeah, 5, right? So I multiply top and bottom by 5, right? So I'm going to get 5 15ths plus
15.
3 15ths. I multiply top and bottom by 3. Does everybody see that? So 5 15ths plus 3 15ths is x to the
8 15.
8 15ths, right? That's my answer, okay? Now, real quick, what is that 8 15ths? That looks a little goofy. We said the denominator of the fraction is the kind of root that it is. So what's that 8 going to do then? Yeah, that's the power we're taking the radical to, right? So really what this ends up being, if I just look at this part in blue, this is equal to the 15th root of x, and if I make the 8 red, it's just that if I wanted to write it in terms of radicals. It's the 15th root of x to the 8th power. Okay? Make sense? All right, so what about this one then? This is no big deal, right? Same numbers, same fractions anyway. What do I do when I divide like bases? We subtract. No big deal, we subtract. So we said before in chapter 6, we always want to keep the base where it has the most power, right? What's bigger, 1/3 or 1/5? 1/3 is, isn't it? When the bottom of a fraction gets smaller, the fraction gets bigger, right? You'd rather have 1/3 of a pie than 1/5 of a pie. Okay, so you end up then, the base stays on the top, and you get x to the 1/3 minus 1/5. 1/3, a common denominator is still 15. 1/3 is how many 15ths? 5. Minus how many 15ths? So 5 15ths minus 3 15ths is
2 15ths.
2 15ths. Done. That's it. Okay, where this gets just a little bit, that's really no trick. Same stuff we did in chapter 6. Only thing that's slightly harder is that they're fractions, but you need to practice with that anyway. Okay, what's a little bit trickier though is if we have a power on the bottom that has a bigger exponent than on the top. Now, what was our rule in chapter 6? Where did we keep the base?
On the bottom?
On the bottom, right? Everybody agree? So this would mean we would write this as 1 over x to the 1/3 minus 1/5. And we just did that. 1/3 minus 1/5 was 2 15ths, wasn't it? 5 15ths minus 3 15ths, right? So that gives us 1 over x to the 2 15ths. So that seems no harder. Why is this harder? Well, because we're not done. If you put that in Moodle, Moodle's going to correctly tell you that it's equivalent to the right answer, but it's not completely simplified. For the same reason that if I asked you to do in chapter 5 something like this, simplify 1 over the square root of 20, you would have broken the square root of 20 up into the square root of 4 times the square root of 5, but what's wrong with that? You can't have a radical in the bottom, right? You can't have a stranded radical, so we had to multiply the top and the bottom by something to get the radical off the bottom, right? What was that? What do you do?
You throw a pie at it.
No, what do you do? I gotta multiply top and bottom by what to get the square root of 5 out of the bottom? Square root of 5. That's it. You multiply the top and the bottom by the stranded radical. That's exactly it. So, and if we do that, what is the square root of 5 times itself?
Nothing.
That just undoes the radical. I just get 5, right? So we end up with the square root of 5 over 2 times 5, which is just the square root of 5 over 10. And that would have been our answer, right? Kind of a pain to do, but that's something we had to do in chapter 5. Well, we have the same problem there. Do you see that? Why do we have the same problem there? Because the 15 in the bottom of an exponent means radical. That's a 15th root, just like this was a square root or a second root. So we have to do the same process. We got to get we can't have a fractional exponent in the bottom of a fraction because that means a radical. Okay? So we're gonna use one of our. We already know this trick, almost at least. We need to make that power of x on the bottom a non-fraction. Okay, now, we don't have the option of making it 0 on the bottom, because to do that, you might think this. You might think, well, let's just put the x to the minus 2 15ths on the top, but that's no good either, because we got to write this in terms of positive exponents. So we're going to have to make the bottom something non-zero, but an integer power. So think of it this way. We've got to bump the bottom up from 2 15ths to the next biggest integer. Well, what's the next biggest integer after 2 15ths? If that's 0 and that's 2 15ths, what's the next integer I run into?
13 will make it.
What's the next, on a number line, what's the next time I hit an integer up here? What's that going to be? If that's 0, what's the next integer? 1. Yeah, there you go, right? So 2 15ths is a small fraction. It's a little bit bigger than 0, but if I add something to 2 15ths, I can get that up to 1. Why is that valuable? Well, remember, when we multiply like bases, we add exponents, right? So what we're really trying to do is we're trying to increase that exponent from 2 15ths up to 15 15ths, up to 1, right? How do we increase an exponent? We just multiply by the same base. so we can add exponents. What does it need to be, Jay?
3/15.
How much?
13/15.
13/15, right? Because 2/15 plus 13/15 would give us x to the 1 on the bottom. Everybody see that? But I can't just multiply the bottom of a fraction by something without multiplying the top also. So I gotta multiply up here by x to the 13/15. So what's our result then? Okay, if we do that, oops, on the bottom, we get x to the 2/15 plus 13/15, x to the 1. On the top, we get x to the 13/15. So that's our answer. We wouldn't write the 1 though, would we? Okay, let's do another one. Try this. What is x to the 3/4 on the bottom, x to the 1/3 on the top? Could we have made this a little simpler? Okay, let me ask you a question here. Do we need to get that x to the 1/3 onto the bottom? No, not really. We don't have to. We did, but did we really need to do that? Did I need to move the x to the 1/5 to the bottom and subtract 1/5 from 1/3? I didn't. I didn't really have to do that. That's sort of a wasted step. Because here's why. Let me tell you why. This is something that, even though the book might not tell you to do this, this is a good trick. Okay, I can already see that 1/3 is bigger than 1/5, can't I? Agree? So I know I'm going to get some power of x on the bottom. And I know it's going to be a fraction, right? So what I'm really trying to do then is get the bottom to an integer power. Why turn it into some complicated number like a 15th in the denominator first? What would I have to do to 1/3? How much do I have to increase 1/3 by to make the power of x 1 on the bottom? 2/3, right? So I could multiply the bottom by x to the 2/3 and the top by x to the 2/3, right? What does that give me on the bottom? X to the 1, so just x. Everybody see that? What about the top? Well, we already did one like this. The top is just going to be x to the 1/5 plus 2/3, right? So what's 1/5 plus 2/3? How many 15ths is 1/5? 3. How many 15ths is 2/3? 10, right? Everybody agree? 5 times 2. And so I'm going to get 3 plus 10, x to the 13/15 on the top. Isn't that easier? Right? You don't have to add that extra step. If you know that the bottom is a bigger power, just move the bottom up to the next integer. Okay? Right? So what about this one then? What are we going to do there? What's bigger, 3/4 or 1/3? 3/4 is, isn't it, right?
Yes.
So then I'm going to turn the bottom is, we know that the base is going to be stuck on the bottom, so let's just move the bottom up to an integer power. What do I multiply top and bottom by? X to the 1/4, right? Because I need to make 3/4, bump it up to 1.
Oh.
Okay? So that gives me, on the bottom, x. On the top, I get x to the 1/3 plus 1/4. What is that? What's my common denominator with 3 and 12? Or 3 and 4, whoops. 12. So how many 12ths is 1/3? 4. So I'm multiplying by 4. How many 12ths? 3. 4 and 3 is? That's it. Okay, no biggie, right? Okay. All right, next issue. Easy. You already know how to do this. In fact, we just did this.
2 square root 5.
When you were asked to simplify radicals in chapter 5, they were all square roots, second roots, okay? But how did you do that, right? If we wanted to simplify a square root, remember our goal was to get as much of the number outside of the radical as possible, and the only way we could do that was the only time we could ever do that is if there was a perfect square factor of the number inside, so 20 in this case. What's the biggest perfect square that divides into 20?
4.
4. So we could split this into a square root of 4 times a square root of 5, and the square root of 4 is 2. So we end up with 2 times square root of 5. Okay, the same trick is what we would use if we wanted to simplify a different kind of radical with a bigger index, like a cube root. Let's try something like this, how about? What if we have the cube root of 32? Okay, now we're not as familiar with these, but now instead of finding a perfect square factor of 20, we're trying to find a what?
Cube root.
A perfect cube factor of 32. Well, let's make a short list of perfect cubes. So 2 cubed is 8, 3 cubed is 27, 4 cubed is already getting pretty big, that's 64. Well, these don't work. The only one that could work is 8. Does 8 go into 32?
Yes.
Yes, it does. So I could write this as the cube root of 8 times the cube root of what? 8 times what is 32?
4.
So my answer then is just,
2 cube root 4.
yeah, 2 times the cube root of 4. Okay? All right. So last example. I want to make this a little bit easier at first. Let's do this without a number. We'll add a number later. Variables are much easier to work with than numbers because the bases don't change and they can't be simplified and they're really obvious. So the goal here is we want to simplify this radical. We want to write it in simplest radical form. Okay, what would you do? Very, very simple. Very simple. If you think, I'm going to give you a trick here, and this trick is gold. This one, I'm gonna call dibs on this trick. I've never heard of this one before. I mean, I'm sure a lot of people have thought of it, but it's a great trick. This takes all the textbooks describe this in such a convoluted, complicated way. But then you can make these really simple. Now watch this trick. Okay, so a cube root is just a 1/3 power, right? Everybody agree? Everybody agree? Okay, so I could rewrite this if I wanted to. I don't really have to, but I could rewrite this as x to the 4th, y to the 6th, z squared to the 1/3 power, right? Everybody see that? Because that's what a cube root means, right? So then if I take powers to powers, right, if I'm raising all of these powers of x, y, and z to the 1/3, I multiply the exponents. So wouldn't you agree that I end up then with, when I do this, the cube root of x to the 4th is really just x to the 4/3, which makes sense. We didn't have to do that because we know that the bottom of the fraction is the kind of root that we're taking, right? Is the index of the radical. And the top of the fraction is just the power we're taking it to. Agreed?
Mm-hmm.
So that's x to the 4/3. This is y to the 6/3. And this is z to the 2/3. Now look at this trick. If we want to know, and really when we're trying to simplify radicals, it's always just a game of seeing what we can get out of the radical and what is stuck in the radical, right? So our answer is always going to have this form. It's always going to be some outside stuff times the radical, the root of some inside stuff, right? So the question is just what goes out and what goes in. Okay, if you take the bases and you write their exponents as mixed numbers, watch the magic. So this is going to become x to the 4/3 is what as a mixed number? Say it again. 1 and 1/3, right? Because 3 goes into 4 one time evenly with 1 left over. So it's 1 and 1/3. So x to the 1 and 1/3, right? Well, the integer part of the mixed number is the part that escapes the radical. So outside, we're going to get an x to the 1. Inside, we're going to get an x to the 1/3. How would we write that though? We'd write it as x to the 1, and there's my 3. There's the denominator, right? You see how that works? Okay, what about the y to the 6/3? As a mixed number, 6/3 is what? Yeah, that's just a plain old 2. There isn't even a fraction part, is there? So this just becomes a y squared, and so outside we just get a y squared and no y's inside, right?
Why?
Because the 6/3 turned into just an integer with no fraction attached to it, right? What about 2/3? Well, as a mixed number, that's just a fraction. There is no integer, right? 3 doesn't go into 2. And so this one just becomes z to the 2/3. So we just write it as z to the 2/3. That's it. Isn't that easy? You can do that without even writing anything down. You can simplify those. Let's try another one. I'm just so proud of that. I think that's so cool. So let's try this. How about if we have the 4th root of x to the 19th, y to the 11th, z to the 12th. Okay? I want you to just see if you can tell me how that breaks down. So what's going to be the power of x there? If it's a 4th root of x to the 19th, that's x to what fractional power? 19/4, right? So if we've got an x to the 19/4, what is 19/4 as a mixed number?
16.
4, yeah, so 4 goes into 19 4 times, right?
4 3 4.
With 3 left over. Gosh, why is this thing writing so slow? To the 4 and 3/4, right? So the 4 goes outside. And then inside I've got x to the 3/4. Done with the x's, right? What about the y's? What's that as a fraction?
2/3.
11/4, which is what is a mixed number?
11 and 2/3.
So 11/4, doesn't that just equal 2 3/4, right?
2/3.
Everybody agree? Right, because 4 goes into 11 twice with 3 remaining. Okay, so then we end up with y squared outside, y to the 3/4 inside. Z, what's the power of z?
Z.
12/4, which is just a 3.
Ring, 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 ring.
Done.
Goodbye.
Amazing, huh? Yeah.
Yeah, you finally were out of this trap.